And today what we're going to do is we're going to continue talking about factoring in the zero product property. Okay, I got a couple of applications for you, and we're going to use some of that knowledge that you guys gained in the first semester to answer some questions regarding functions. So with that being said, you look at this example, and several of you, if not all of you, at least here in class, I've seen writing this down. You look at this first function. What kind of function is this? Can you qualify it? I know there's three terms. It's a trinomial, but what type of function is it? It's degree 2. What do we call a degree 2 function? Louder. Quadratic. Good. And a quadratic function, do we remember what the shape of it is called? It starts with a P. It's a parabola. Okay. So this is some general knowledge that we should have whenever we see something that's like an x squared function. Okay. That's called quadratic. And its shape is going to be a parabola. Now, there's a couple other things that we remember, at least we should remember, about parabolas. And that is that when you're in the form ax squared plus bx plus c, we call this our standard form of a quadratic function, okay? A is called the LC. What do you think the LC stands for? Number in front of the variable is a coefficient. And because A is the one that comes in front of the first term, it's called our leading coefficient, right? You guys remember the term leading coefficient? Y'all are sleepy this morning. Well, remember that if the leading coefficient is positive, if A is greater than 0, then our parabola is concave up. I call that field goal is good. Positive thing, you can see smiley face. You know, these are basic mnemonic devices. If the leading coefficient is negative, if A is less than 0, call it swole patrol. Okay, that's where it's concave down. You could draw a frowny face, if you will. And real quickly, about a parabola, you can determine its concavity just by looking at the LC, looking at the leading coefficient. Okay. Now, for example 7, what is the leading coefficient, Drew? Son, there's not even a 6 anywhere in this function. Coefficient is number. 0 for 3. The number in front of the term of highest degree on this one is 1. It's an implied 1. That's what we call our quadratic coefficient, okay? So the leading coefficient is the number in front of the x squared term. And if we don't see a number there, it's implied to be what, class? It's implied to be 1. Okay. Now, the quadratic coefficient here being 1 tells me, Luke, is this concave up or concave down? Try again. Good night, America, people. What is wrong with y'all today? Y'all are some zombies. You're not paying attention. Wake up! All right. Let's try that again. Leading coefficient test says, oh, look, we got a positive leading coefficient. Field goal is good. That's a positive thing. Smiley face. This parabola is concave up. Now, all of that being said, okay, I'm going to try to sort of piece together what this function is going to look like, okay? Now, I'm going to highlight in green over here this number -2 because that's going to be a special number for our function, okay? That's going to be what's known as the Y-intercept. Now, right here, this point has an x-coordinate of 0, okay? Anytime I plug in 0, I'm going to get the Y-intercept, and plugging in 0, you guys have seen me do this before, is very, very easy. We just do the cover-up principle. It would be as though I plugged in 0 for both of those x terms, and y winds up being -2. Okay, again, I'm reviewing. This is some review from first semester. So all of that being said now, we're going to get into part A, which says, hey, find x when the function equals 6. What does that mean? That means, hey, let y be 6, and we want to find, I'll just make it up here, we want to find what is the corresponding x value when the y value is 6. Okay, and I don't necessarily know, oops, let's try this again. Here's the magic of OneNote. We don't know where this point is going to be up here at y equals 6. It could be over on the left, it could be over on the right. We don't know where it is. We're asked right now to solve for whatever that x value is. So we're going to let y equal 6. Okay, it's important for you guys to also note that f of x is the same thing as y. Okay, so when we see f of x equals 6, that's the same thing as saying, psst, let y equal 6. Okay, and so we, instead of f of x equals that expression, we've got 6 equals that expression. X squared plus 2x minus 2. All right. Now, fellas, last week we talked a lot about solving quadratic equations. I just wrote up a quadratic equation. Y'all see my pretty pink camo Band-Aid right there, by the way? Nice. I'll tell you how I got my Band-Aid. As you guys are contemplating that quadratic equation there, I was making some oatmeal yesterday at the campground, okay? Had some boiling hot water. And I went to pour the boiling hot water, and I missed the bowl. Y'all are probably like, you idiot, what are you doing? I've missed the bowl and poured it straight on my finger. You know what boiling hot water does to skin? It hurts it. My skin literally cracked and peeled right off. It was disgusting. And my kids looked at me like, why are you mad? Why are you screaming? You're making oatmeal. What the heck is wrong with you? They were watching Scooby-Doo in the camper yesterday morning while I was burning my finger off. But anyway, I digress. Now I'm wearing a pretty pink camouflage Band-Aid and all as well. Last week, Grove, we said that a quadratic equation, you could use what's called the fundamental theorem of algebra. How many answers are we going to have on this equation? We're going to have 2 solutions. Do we remember that? It's a degree 2 equation. So we're going to have 2 solutions. Okay. Now, who could tell me my first step in finding those 2 solutions? Paul. Nice and loud for me. Very good. In our plan, we're thinking, George, we're going to use the zero product property, and I don't see 0 on the equation yet. So Paul is absolutely correct. We're going to subtract 2 from both sides, and Mr. Booth is going to tell me what that's going to get on the right-hand side. There's more than 4. There's an x squared. I'll spot you that. What else? Why is it negative 2x? All I'm doing is subtracting 6 from both sides. Wake up. Plus 2x. I still don't see where you get negative 4. What's negative 2 and negative 6?
Negative 6, negative 8.
Negative 8. Tell me why it's negative 6. Or you might not know. All right. It was positive 6 over on the left. Okay. So Will, tell them why it's negative 6. It was positive 6 over on the left, and Paul told me I wanted it to be 0. What do I do to positive 6 to make it 0? If it's already positive, what's the inverse operation of positive? We subtract 6. We're going to subtract 6 from both sides. I feel like there's a disconnect. Are you guys okay today? What's wrong with you guys? Y'all took a 3-day holiday and everybody forgot how to add, subtract, multiply, and divide real quick. Okay, I see how it is. I got my work cut out for me today. That's okay. Andrew, you're going to make it all right. Factor this trinomial for me. I'm going to keep putting you guys on the spot.
X plus 4, x minus 2.
You have redeemed my hope in humanity, Andrew. Very good. All right, so he factored that out. Remember, to factor something is to write it as a product. All right, and now we can use the ZPP, the zero product property, which tells me, ooh, can we do this step in our head, Jack B? Jack's like, oh, yeah. Scrooby snacks. All right, what 2 answers are we going to get?
Negative 4 and positive 2.
Fabulous. X equals negative 4 or x equals positive 2. Now, what did we say, Quentin? We were looking for. Do you remember what we were looking for in our graph? It's in orange, right? The point where y equals what? The point where y equals 6. And so we just found both of those points. We found it happens at negative 4, and we found that it happens at 2. And that should make pretty good sense, because what shape are we drawing? We're drawing a parabola. And remember how a parabola does one of these right here? That's exactly what we just found. Is it okay to have 2 solutions to an equation? Absolutely. I think I used the, by the way, we did part B there in the graph. Thank you, Quentin. I used maybe last week, the week before last, an example. Like if I threw a ball up in the air, if I threw a baseball up in the air, and I gave you a quadratic equation that would model its height at time t seconds after I release the ball, right? At how many times will that height be, let's say, 10 feet? Why twice? Once it's going up, once it's coming down. That's quadratic. That's a parabola. If you were to graph it out, its height. And actually, you know, when we talk about projectile motion, did you guys know that every projectile travels in a parabolic arc without, you know, major influencers like wind and things? Think about it. Like if you're playing basketball, when you shoot a basketball, what shape is that shot going in? It's going in a parabola. Okay. No matter how hard you try to make it not go into a parabola, right? You shoot it, it's going in a parabola. Thanks to what? Gravity. When you throw a football, when you hit a golf shot. Now a lot of golf shots, you know, have this fade or have this draw or whatever it is, due to spin, right? And wind blowing and whatnot. When you shoot a gun, guess what that bullet does right when it exits the muzzle? It actually rises a little bit, and then it falls. Isn't that trippy? And guess what? Its shape is starts with a P, ends with a parabola. All right. Quadratic functions model a lot in this world. Okay, there's a lot of neat applications that you guys will see, but we got to get there first. Let's try one. You guys try this one on your own. Goodness knows you might need some help with it, but I'll let you struggle for a couple minutes. Maybe y'all can surprise me this morning. Stupid thing coming. Again, what we're doing is we're replacing f of x with 7, solving the resulting quadratic equation, and then determining what that means graphically. And you don't have to graph the parabola out on this. You really don't, I promise. Just tell me what your answer, sort of interpret what does your answer mean. Somebody getting hot in here? That heater is blowing right over the top of my little screen, warming me up good. Take about 30 more seconds. Lewis, you sleepy this morning? You and me both, brother. I did a bad thing. I stayed up too late last night playing a video game. You guys ever do that? Mrs. Morgan was reading her book, and I was playing my video game, laying there in bed. I stayed up till, I think, 1:30. Shame on me. I was playing Breath of the Wild, Zelda Breath of the Wild, and just got, you know, sidetracked. I realized there's this new thing I can find that I haven't found before, so I was tracking it down. It was pretty fun, but I'm paying for it now. That's how it goes. All right, Joey, just right off the top, did you get a couple answers? What'd you get? -3 or +5. Charlie, do you concur with that or do you disagree? Charlie concurs. Anybody else? Anybody concur? All right, let's see how that shakes out. You might have amazed me, that oh boy. We replace f of x with 7, so we're going to solve the equation 7 equals x squared minus 2x minus 8. All right, we do what first? Subtract 7 from both sides. 0 equals x squared minus 2x minus 15. And it looks like x plus 5. No, x minus 5. One more. There we go. Minus 5 and x plus 3. Because those factors had to have different signs since the 15 was negative, and we wanted the bigger one to be negative since the 2 was negative. All right, and then the ZPP tells us x equals 5 or x equals negative 3. Is that what you said, Joey? Attaboy. All right, graphically speaking, again, remember, what does that mean? That means that here we've got some parabola. Its y-intercept is going to be negative 8. We can easily tell that from the cover-up principle. And then up here at the top, it's going to have these 2 points right here, negative 3, comma 7, and over here, positive 5, comma 7. Whoops, that was terrible. Again. Whoop. There we go. And there's our little parabola. Okay. Now, there's a couple of special points that we did not find. Okay. Look at that picture. Actually, you can look at both of the pictures. The one that we did earlier, example 7, and the one that we just did. Real similar examples, by the way. But what special points on those graphs did we not find? The X-intercepts. Now, I want you to scratch your head for a sec. I want you to think with me. What process could I go by, similar to what we just did in those 2 examples, to find the X-intercepts? Tiago, take a step. If you get it wrong, it's okay. This is a good thinking question. Think. Go ahead. A process similar to what we did a moment ago to find the X-intercepts. Tell us what you're thinking, even if it's cuckoo Cocoa Puffs. We'll still love you. Nothing? All right, Jake? Let f of x, which is also known as y, equal 0. Okay. Now, this is our last example for the day, and we're going to do just that. Okay. We are going to find what are called the, quote, zeros of this function. Can you write down your notes? And I think you got this last week as well. But there are a few words that I will use interchangeably when we're solving equations. The zeros, the roots, the solutions, the X-intercepts. All of these in Algebra 1, I will just kind of use interchangeably. So when I say, hey, find the roots of this equation, or find the zeros of this equation, or find the X-intercepts of this equation, or find the solutions of this equation, I'm asking the same thing every time. It just means set your equation up and solve it out. Now, what Jake just recommended that we do, that's exactly what we're going to do here. We're going to let f of x equal 0. We're going to have 3x squared plus 10x minus 8. We're going to have to solve that out. Big Nate, game on. What's your factoring method that you're going to use here? Did y'all catch that reference, by the way? No? Okay, never mind. There's a series of children's books called Big Nate, one of which is called Game On. Magic method, that oh boy, game on indeed. Okay, see if you guys can do your magic method. I told Teddy Morgan, the 9-year-old, this weekend, well, I told him at the end of last week. I said, son, I had a sad realization. I was in Kroger, and y'all know Kroger sells books. Kroger's got a little book aisle, cards and greeting cards and things like that. Anyway, I saw that there's this new book in this series that it's called Dog Man. Anybody ever seen Dog Man? You don't know about Dog Man? It's by the same creators who wrote Captain Underpants. Did you guys ever read Captain Underpants when you were younger? So anywho, Teddy Morgan, the 9-year-old, used to love Dog Man books, and he's probably got like 7 or 8 of them. And they always have like a pun in the title, okay? And I can't think of one off the top of my head. Like Call of the Wild, instead of Call of the Wild, it's like Brawl of the Wild or something like that. Anyway, the little puns. And this newest one has come out, and I thought to myself when I saw it, I used to buy that for Teddy. I'd buy a little $7 book. And then I thought about it and I said, you know what, he's probably too old to enjoy reading this book now, because on the cover it said it was like for, I don't know, 4 to 7-year-olds, something like that. And so I got home, I told him, I said, son, I thought about buying you the newest Dog Man. And then I got sad because I thought, you're growing up so fast, you probably don't like Dog Man anymore. And he said, Dad, I love Dog Man. I'm like, yes. He's still sweet and innocent. All right, Mossy, I don't think I've asked you a question yet. You got this factored? Joe, how about you? No? Magic method, I'm striking out. Reed? All right. Mossy, how can I check to make sure that Reed did that correctly? Good. We're going to FOIL it out. Absolutely. Now, look, I'll be honest with you. The first and the last, not so important. Okay? Because obviously the first is 3x squared and the last is -8. The important one is the outer and the inner. Okay? Luke, what do you get when you do the outer and the inner? Pardon? All right, so the inner is 12x. And what about the outer? What kind of 2x? Attaboy, -2x. And so class, 12x and -2x? Congratulations, Reed. You factored it correctly. Now, are we at the point, guys, where we can do this next step in our head? Can we get our answers, Jack? Candiato, what are they? Good. Or, and this one's the one you got to stretch a little bit for. X equals what? Over 2/3. Good. 2/3. Now, mentally, here's the mental gymnastics that we're doing right there. We are envisioning in our head 3x minus 2 equals 0, and we're saying, all right, 2 steps. What do I do to get x by itself? Add 2 to both sides, divide by 3, 2/3. Okay? Just that simple. Now, those are the 2 roots, the 2 zeros, the 2 solutions, or somebody said X-intercepts. All right, so we just found, graphically speaking, we just found where that function crosses the x-axis. By the way, is this function, Joey, is it concave up or concave down? I'm sorry, I didn't hear you. Concave up. How'd you know that? Or was that a lucky guess? That 3, it's our LC, our leading coefficient. And it is positive. Smiley face. Ding. You can't see me smiling. Kind of with my eyes, I guess, maybe. We do smile with our eyes. All right, so that's concave up. So here's what we've just found. Let's see, who can I pick on? I'm trying to call on everybody. Who have I not called on yet today? I don't know. I've called on everybody. James, what's the y-intercept on that function, real quick? Cover-up principle. We're plugging in x equals 0, so we cover up the 2 x terms. What does y equal? -8. Good. All right, so down here is the y-intercept, 0, -8. Okay. What did we just find, Alex? What 2 points did we just find? Not the y-intercepts. We found the x-intercepts. There's 2/3. So 2/3, 0. And what? -4? -4, 0. Okie dokie, artichoke. Y'all see what we just did there? We found the x-intercepts by solving the equation, and we found the y-intercept by plugging in x equals 0. Alex, which of those two endeavors did you find more challenging? X-intercepts or Y-intercept? Absolutely. Every time, fellas. Can we make a note to that effect? That finding the X-intercepts is always going to be more challenging. Let's find the Y-intercepts. All you do is just plug in X equals what? X equals 0. And BT dubs, I didn't mean to say Y-intercepts plural. Y-intercept is singular. Because in order to be a function, it has to pass the VLT. It has to pass the vertical line. Woo! Coming in off the top ropes with that one. That a boy. No hesitation whatsoever. Vertical line test. So we can't have two Y-intercepts. That would be silly. Okay? But we can have, and we do in this case, have two X-intercepts. Is it possible? Ooh, little thinking question here. Is it possible to have a parabola that doesn't hit the X-axis? How so? Describe said parabola. Raise your hand. Tired of hearing from Jake. Someone else. Tiago. Yeah, but we're talking vertical parabolas. Describe for me. Ooh, I'm not letting you off the hook just yet. Tiago, describe for me the parabola, and it's not up on the screen, so you don't look at the screen. Describe for me the parabola that would have no X-intercepts. Use words like concave. Use words like below or above. Use a special V word that describes a special point on the curve. All right, you used none of those words that I asked you to, but you adequately described it, so kudos. Paul, you want to polish his answer up a little bit? Okay, you did the exact opposite of his answer, but you answered correctly. Again, I'll put it in both of you guys. See, I'll tag team it. If the parabola is concave up and its vertex appears above the x-axis, guess what? It ain't hitting the x-axis. No x-intercepts. If it's concave down and the vertex is below the x-axis, right? What am I looking at visually? What that looks like is something like that right there. Or, you know, something that looks like that. Of course, there's no x-intercepts. So what, your pistons ought to be firing in your heads right now when you think about what I just drew out. Y equals ax squared plus bx plus c. And how did we say you go about finding x-intercepts? You make the y what? Okay, I'll play your clever games, you rogue. I'll make the y 0. Now, what deadgum kind of equation is that? Starts with a Q. Quadratic. And what does the fundamental theorem of algebra say about all quadratic equations? They have two solutions. And what's another word or phrase for solutions? Pardon? Answers? Okay, yeah. What else? Gosh, doggy, I'll quit mumbling. Loud. Be proud. Roots, zeros, answers, solutions, aka, we got graphs on the screen, by the way. What's the one that I didn't say?
X-intercepts.
Attaboy. X-intercepts. So you're telling me, dadgummit, Coach Morgan, that equation right up there is supposed to yield two X-intercepts, and yet my graph that Tiago and Paul somewhat adequately described, that parabola doesn't hit the X-axis at all? Okay, how can we make sense of those two seemingly contradictory statements? Jack, you want to take a stab at it? No, I tell you what, since I'm almost out of time, I'll let this cat out of the bag. You guys could totally solve this equation once you have Algebra 2, because there's going to be two what are called non-real, or aka imaginary, make sure I spell this right, imaginary roots or zeros. How the dump are you not writing that down? That's outstandingly interesting to me. That boggles my mind. You know, when we talk about the fundamental theorem of algebra, it doesn't say that every quadratic equation is going to have real answers. It just says every quadratic equation is going to have two answers. And in this case, if as Tiago and Paul described it, the parabola doesn't hit the x-axis, so what? There's still two answers. They're just imaginary, which is kind of kooky when you consider mathematicians just imagined it and just like made it up and created math to suit their needs. And that's actually what mathematicians do quite a bit, right? They and you guys, not to beat a dead horse here, but they encountered this equation a long time ago. Okay, they encountered that equation. And that's a very basic quadratic equation. They said, man, we could do so much in engineering applications and in sciences and in physics if we could just figure out how to make this equation have a solution. All the other quadratic equations that we encounter, we have solutions, but when they look something like this, that we just throw our hands up in the air and say, sorry, can't solve it. No more. I'm tired of that. We are going to solve it. And so what they did was they subtracted 1 from both sides. They took the square root of both sides. And then they focused in on this part and they said, you know what we're going to do? We're going to define a new number. We are going to call this number I for imaginary. And so they said, forever, now until the end of time, I, a little lowercase curly I, is going, cursive I, excuse me, is going to equal the square root of -1. And then they built this whole branch of mathematics off of that called complex analysis. And then they were able to solve equations like this. They were able to say that parabolas like this, although they didn't hit the x-axis, its equation could be solved and you could find both of the roots. They would just be imaginary roots. And life was good. You guys will learn a lot about that in Algebra 2, okay? But I got all geeked out and excited about it today. So anywho, we answered the basic question here about our points on the parabola, so you can go home, I guess, or go to school, I mean. And hey, we will not meet again until Friday. Tomorrow's Wednesday. We never meet on Wednesday anyway. Thursday, I've got senior retreats again. Remember, look on where? YouTube. Look on YouTube. I'll have you a lesson ready for Thursday. Live Jesus in our hearts. All right. Thank you, fellas. Y'all take care and have a wonderful, wonderful day. Can't believe y'all didn't get excited about imaginary numbers like I do.